In this video, we are going to learn about how to create a schematic symbol and PCB footprint for 817 opto-coupler IC. It is so-called PS817 or PC817 based on the manufacturer. It is also called as photocoupler, so do not get confused with the opto-coupler and photocoupler name. Both are same. Hi everyone, I am Vaibhav Sugandhi, co-creator at Linked Frequency. This video is divided into 4 important parts. First one is understanding and downloading the right datasheet from the manufacturer website. Second step is to create a schematic symbol using IEEE standards and user friendliness or user interface as a priority in EasyEDA. Third step is creating a PCB footprint following IPC standards and also a Cartesian geometry in EasyEDA. Last but not the least, fourth step is to create and combine the PCB footprint that we have designed with the schematic symbol and make it as a component library so that you can use it in your future project. So let's get started. I have downloaded the datasheet from the original manufacturer of 817 IC. There are several manufacturers and even more than 10 different manufacturers in this particular IC segment. So do not get confused with a different brand name or a different manufacturer. Whichever manufacturer you are considering, make sure that you download the true datasheet. In this case, I have downloaded from the Opto Supply, which is a company name, and they have IC in SMD as well as through-hole version. Through-hole version IC is called PS817, wherein SMD version of the same IC is called PS817-SMD. In this datasheet, we will see a lot of detailed information which are recommended and required for the designing a circuitry. But what we are interested is in this particular section, which is all about schematic representation and also PCB footprint details, dimensions basically. And using this data, we are going to create a schematic symbol and PCB footprint. So let's head towards the EasyEDA and start with schematic symbol. Now in this EasyEDA, I will go to the file section and create a symbol. So this particular IC is pretty much simple compared to the any 555 timer IC that we have designed in previous tutorials. If you have not watched that video, please go and watch that video so that you can understand this one very easily. If not, then you can continue with this video and still watch it and then go back to 555 timer IC. It is not having any dependency. So first thing is we are going to bring the pads or maybe the connecting points, which are so-called pins actually, 1, 2 and 3, 4, right? So I will organize them in such a way which is given in the datasheet. You can see here the first pin is anode part of the LED inside the opto-coupler, and the second pin is the cathode of that particular LED, and third pin is the emitter, and fourth pin is a collector of that particular transistor inside, phototransistor basically. So this pin number or this pin numbering has to be managed properly, which because pin number 1, 2 and 3, 4 should be kept in this order only. So what I will do, I will drag these 2 points here. I'll just try to arrange them with a 10 mil grid size, and let's name them properly, which is a necessary point. after doing a several trial and error, I can do this much of design at this point of time, because the limitation with respect to the grid size, which is going to be 5 mil at the maximum at the bottom side, you can make it 5 mil, not below that. Because of that reason, we cannot create this arrow very good way or very aesthetically good, but it indicates the phototransistor much better way, and collector and emitter is indicated properly. Anode cathode of the LED is also indicated properly. Considering those things, I'm okay with this particular design. And notice that whatever we have drawn here, which is all systematically and symmetric. Why? Because it is essential to make sure that your entire schematic symbol is followed with the IEEE standard, as well as systematically arranged properly, symmetric in all the direction. That makes it a professional schematic symbol design. So I will change the color of the border, which is all about this color, which is a standard color that we know, and I'll save this particular file. So in my account, I'm going to save it. And what is the title for this? Of course, we are going to follow the name given by the manufacturer, which is PC817. And who is the supplier? Supplier right now we are not sure about it, so I'm not going to worry about it. But manufacturer, we are very sure Opto Supply is the name of the manufacturer. So Opto Supply is the name of the manufacturer. And then what is the manufacturer part number? It is PC817. And link you can provide, or you may skip it. Choice is yours. In this case, it is Opto devices, Opto electronic devices. So I'll give a tag as Opto devices. And in description, I can write a small description about this particular device. And this is all about the description. So I'll save it. And once we are done with that, what we need to do is we need to go to this custom properties section, where we have to make sure that add to BOM is yes and convert to PCB is yes. Name is given, footprint, we will attach it later on. And prefix or designator should be U ? Because this is integrated circuit. That's why U is the prefix. And then supplier is unknown, and other parts are already discussed. So once we are done with creating a schematic symbol, next step is to head towards the PCB footprint design, and we can do it now. Before jumping into the PCB footprint design, we have to understand the dimensions of this particular PCB footprint, which we will do it by using the reference of this particular datasheet information. So let's get started with that. Here we can see that the total distance from one pin to another pin vertically and horizontally is given. Now using this data, we can create the Cartesian geometry data in our PCB footprint design. It's absolutely same as our 555 timer IC's design. I think if you have understood that part, this part is quite easy to you. But still, I'm going to explain to you at the first time. So see here, the data from this point to this point is already given to us, which is a 2.54 mm. And this is same as for the other side as well. This side 2 pin and these 2 pin, both will be having a 2.54 mm pitch. The point is, what is the distance from this point to this point? We have a maximum distance here, and we have a minimum distance here. Minimum distance is from this edge, and maximum distance is from this edge. And this bend, whatever we are seeing here, it is easy to bend it when we are soldering that IC. But we will consider something which is very technically right, or you can consider which is very easily computable. 7.62 mm is the minimum distance, which is technically computable. Why I mean it is technically computable means, if you go to the calculator, I'll explain to you. So if you go to the calculator, you can see here in calculator section, so whatever we have is a 2.54 mm into 3 is 7.62. If you add 1.27 to this one, it is 8.89. This 8.89 is the standard value in PCB industry. If we consider this value rather than considering a 9 mm or maybe even with respect to 7.62 mm, this is better one. So 8.61 or 8 how much it is? It is going to be 8.89 is the value which we have to consider for the distance from one side of the pins to the another side of the pins. These are the two values, and using these, let's design the PCB footprint. Now I am on EasyEDA, so I'll go to the file section, create a new footprint. Here I will bring 4 pins and keep them in a same sequence. I hope you understand this sequence very importantly. Why? Because first pin, second pin should be on the left side, and the third pin should be on the right side bottom, and fourth pin should be on the top side, because this is how in a data sheet they have organized the numbering. If you change the number, then your entire schematic symbol and PCB footprint linking will be in a wrong direction. That will create a lot of problem when you go for the application design. So that's why maintain this numbering. Now what we will do is I'll select the first pin and make it as a rectangle one. It's actually a square one. You can make it as a rectangle one as well. And when you go back to the data sheet, you can see the width of the pin, or the diameter, or you can say the drill width which we require, or drill diameter which we require to insert this pin is minimum is 0.5 mm. But we will not go with a 0.5 mm. So we will consider 0.8 mm as the drill hole, because it's good to have some tolerance. For 0.8 mm, you can create a pad width of 1.2 mm if you feel it is comfortable. If not, you can go for 1.6 mm as well. If you are having high power optoelectronics, or somewhere around 100 milliampere of switching voltage or switching current or load you have, then on that time it is better to go with a little bigger pad size. That will protect your opto-coupler getting short with respect to the current flow and all that thing. And it is easy for soldering as well. So I'll select all these three pads and change the width of the pad or the diameter of the pad to the 1.6 mm and drill hole to be 0.8 mm. Alright. And I'll select these two pads, or you can select these two pads and set as a y-axis to be 1.27 mm, which is very well known to us because total distance is 2.54 divided by 2 is 1.27. So again, in the y direction with respect to negative side, it is 1.27 mm. Now we need to arrange the x direction. I can select both of them and arrange it at the same time. That is also possible, or you can select one of them and then arrange them. So the total distance what we have is with respect to the width of the entire pin positioning is 8.89. And if I divide it by 2, let's confirm whether it is 8.89 or not. 7.62 is the number which we know, or you can go for 2.54 as a standard number. Into 3 is 7.62 plus 1.27 is the multiple of 1.27 in all the direction. So that's why it is better to keep a 8.89. And divided by 2 is 4.445. So it is why it is necessary to use a calculator, even though it is a simple calculations. For this reason only, 4.445 accuracy is required for us after decimal 3 digits. Okay, I'll select both of them. I will make a x-axis as minus 4.445. All right, and on the positive side, or on the right side of this x direction, I'll make it as a 4.445 positive side. Okay. This is how our opto-coupler is designed. Now the pad placement and the footprint design is completed. What about the body? Which we can do it by using a datasheet again. If you go back to the datasheet, you can see the width of the body is 6.4 plus or minus 0.5 mm tolerance. So I'll consider it as a 6.5 at this point of time, but let's verify it whether it is possible or not possible. And the height of the body, you can say width and height interchangeably according to where you are looking in your perspective. So this one is somewhere around 4.6. This is 4.6. That one is 6.4. Interchangeable numbers. That's a good one, right? So I'll come back to our EasyEDA. Go to top silk layer. Use a simple rectangle tool also possible. Otherwise, you can use the wire tool to create a lines and use a Cartesian geometry for that. I'll use a Cartesian geometry for that. Alright, this is how we are going to design our body of opto-coupler by using the datasheet information. According to datasheet, we have drawn the border using a Cartesian geometry and wire tool on the top silk layer. Once we are done with that, I have given this small indicator as a pin number 1. Of course, we have a square pad here which indicates it's a pin number 1, but along with that I have given this indication. Why? Because in datasheet they have given anode indicator. So it's always better to give this extra indication so that the manufacturing people or the assembly person will get to know where is the pin number 1, because it is swappable. You can place this IC like this also, you can rotate it and place it like this also. To avoid that misplacement, we need to give this particular indicator. Plus pad is also extra indication so that they can double confirm if any one of them are not clear to them. So this is how our PCB footprint is designed. Now we will save it. But what is the name for saving this one? And this particular IC or this particular footprint is dedicated for PS817 only. It is not a dual inline package generically. We can call it as a dual inline package with a 2-pin, but it's better to give a specific name as per my knowledge. But if you feel to give a dip here, you can give that actually, not a problem. I think we'll go with that one only. I'll name it as a plastic dual inline package, PDIP, and hyphen 4-pin. This is very important because if it is a 8-pin IC, then PDIP hyphen 8P is necessary. If it is a 4-pin IC, then PDIP hyphen 4P is necessary. And then tag is always a DIP IC, so it is not opto-coupler related. So we'll give it as a DIP. And we have created that DIP category of tag in last video. That's why it is already there. And 4-pin opto-coupler not necessary. So what we can do is we can change it, make it as a 4-pin plastic dual inline package. Alright, so this is how our PCB footprint need to be saved. And when I click on that save, we are done with designing the PCB footprint for opto-coupler. Now it is time to go to the schematic symbol and combine the schematic symbol library and PCB footprint library together to create a component library. How we do that? We'll go to the schematic symbol that we have recently designed and then click on the footprint section and search as PDIP-4P. That is what the name we have given, right? And we can see that particular library is reflecting us. So double click on that and you can see that it is both are attached. Just ensure once again pin number 1 and pin number 3 are matching properly. Why? Because if you've given a wrong pin number in the pad selection, then you can still correct it at this point of time. If you do not recognize it at this point of time, it will create a problem when you go for the application design. So I'll just go back to the our data sheet and just cross verify pin number 1, 2, 3, 4 are like this. And according to the data sheet information, we have pin number 1 as an anode, pin number 2 as a cathode of that LED, and pin number 3 as an emitter, and pin number 4 is a collector. C on the collector side and C on the cathode side of the LED may be confusing as a letter, but by symbolical representation, we are very sure that they are different and they are dedicated for their own application. So considering this, I'm done with designing. So I'll just click on the update footprint once again to ensure, and we are done with creating a component library for opto-coupler, which is naming PS817. Wonderful. I believe you have created your component library of PS817 by watching this tutorial. If you have any questions or feedback about these tutorials, feel free to comment down below in this video. See you again in the next video. Until then, tune yourself to make a difference.